topics. As you can see, provenance and Internet of Things are mostly used keywords. This is natural because these are our search strings. And blockchain, security, and cloud computing are other keywords. What are the main problems being trying to find a solution for the IoT using data provenance? Data provenance is primarily used to solve security, privacy, reliability, and trust-related problems. We can say that the studies in these fields have increased throughout the last years. And blockchain is frequently used to provide data provenance. Question 4 was, what are the open issues and the future research directions of data provenance and the Internet of Things? In the IoT and data provenance studies, security and privacy are often the natural subject of the study, even if it is not the main topic of the study. IoT devices have some security difficulties due to resource constraints. Therefore, it may be necessary to take additional precautions to ensure security in IoT devices. And privacy is an essential issue in IoT applications because it often senses information from environments. Data provenance can provide security, reliability, and trust in IoT devices from a data provenance perspective. However, data provenance can provide these features while at the same time creating disadvantageous situations because data provenance provides not only the current state of the data, but also the origin, the stage, and the processes it undergoes, the information such as when and by whom these processes are performed. Therefore, this information may also create privacy issues. Security mechanisms such as encryption and authentication are required to restore privacy. The issues of security, reliability, trust, and privacy in IoT devices and data provenance are open issues, and that will continue to be worked in the future. Conclusion, we presented an SLR-based method on data provenance in IoT. We investigated the challenges encountered in IoT applications and worked on the use of data provenance as a solution. The database search took place on October 2021, and we conducted a literature research covering the years, the last 10 years. We found 140 published papers. After applying exclusion criteria for these papers, we have focused on the final 16 papers. The provenance is primarily used to solve security, privacy, reliability, and trust-related problems. We can say that the studies in these fields have increased towards the last years. And blockchain is frequently used to provide data provenance. Regarding the SLR-based method, we may not have analyzed all available studies. It is impossible to ensure that all studies are considered. And our research ended in March 2022. Here you can see selected papers, a list of selected papers, and references which we use. That was my presentation. Thank you very much for your listening and attention.
Perfect. Thank you, Professor Emrullah.
Thank you
for your presentation. And maybe there are some questions or consideration from colleagues here connected.
Oh, yes. I'm Alberico Sonnessa from Politecnico di Bari. Good evening, Professor. I've got just a curiosity about the exclusion criteria in maybe the second or the third slide.
Yes.
Can you move to the slide, please?
Yes, yeah.
Okay. And not having a quality aspect of publication, how did you assess the quality of the publication? In an automatic way, by reading the paper, by using the impact factor?
Actually, that we have read by reading the papers and the articles which are reviewed in this digital databases are mostly having these quality aspects, and therefore actually we couldn't have any papers which didn't met these aspects, because they are reviewed, and so they are non-prestigious libraries. And after that, we have read all of them, and we have we looked at if they have implementation and simulations and enough information about the problem and solution.
Thank you very much. Okay.
Thank you.
Yes, I have also one more question, because I was intriguing about the fact that, of course, data can be altered during the life cycle, you know, and I was wondering if in literature there is a clear taxonomy to differentiate data provenance, if it refers to the very first origin of the data, or the last sender of the data, or just it is possible, as you have mentioned, track the whole process and passages. And in this case, what are the methods that we can rely on?
Actually, we can have all information about it, but some information maybe are not sufficient for our research. That depends on problem actually. And for example, someone have a blockchain based data provenance framework for IoT, and they want to see if a vaccine procurement is out of date, for example. For them, is only the date and the temperature of this vaccine is important. As I said, it depends on problem and solution.
Thank you. Thank you to Professor Emrullah. And I suggest we move forward. And I will introduce the work from Professor Prestileo, Mascitelli, Meli, Petracca, Giorgi, and Melfi. And let me see who's there to present.
Yes, I'm going to present it.
Okay, perfect, Professor Dietrich. And they will present a contribution regarding the resilience of cultural heritage in extreme weather conditions. And this is an interesting case study. Please, I leave you the floor.
Okay, thank you. Good afternoon. I am happy to be able to contribute to the conference by presenting this work. We move in Sicily, in the center of Sicily, where is the UNESCO archaeological site of Villa Romana del Casale. It contains beautiful mosaics and frescoed walls. An example of is in the center of the slide. These features for centuries have been subject to the attacks of bad weather and hydrogeological consequences. We will show what was the response to the occurrence of the Apollo Medicae that in October 2021 devastated the surrounding area. The authors come from different institutes. We at the Institute of Atmospheric and Climate Science of the National Research Council have been supported by Civil Protection Department and by the Italian Air Force. Contents, we move to an introduction, a historical introduction with the site description, and then move to look at the Apollo Medicae through the ground and satellite data analysis with some words about the resilience of the archaeological site. The villa is the UNESCO World Heritage List. The motivation is that the villa is a sublime example of a luxurious Roman villa due to the exceptional nature of its mosaics. The Villa del Casale was a residential building from the late 4th century. It was built on the earlier rustic villa from the 1st to 3rd century. The site was, with some changes and transformation, inhabited continuously until around the 12th century, when a powerful flood covered it and consigned it to the oblivion. In the 15th century, there is evidence of a village called Casale, built on the top of Roman ruins and on the top of early medieval Arab settlement, later inhabited by Normans. Also, this rustic village was also destroyed by successive floods. At the end of the 18th century, the emerging ruins of the Contrada Casale began to attract the interest of some antiquarians and clandestine diggers. But another flood occurred in the early of 19th century. After this event, the first official archaeological excavation began, but it was not until after the Second World War that Gino Minicio Gentili conducted the most comprehensive work of site discovery. Between 57 and 67, Franco Minissi realized an innovative architectural solution for the time, closing the perimeter wall and restoring the ancient volumes to the Roman villa. But this solution, although valid in the design idea, soon turned out to be disastrous from the conservation point of view for the mosaic floors and wall paintings due to the material used, due to the progressive deterioration over the years and to the microclimatic conditions that were unsuitable not only for the conservation of the artifacts, but also for the well-being of visitors. After that, the site suffered considerable damage in 1990, in particular a flood in October 1991, exactly 30 years before the Apollo Medicane that we are going to describe. The gradual deterioration of the roofing system, which was highlighted with greater attention, activated the Regional Center for Planning and Restoration, Department of Cultural and Environmental Heritage and Public Education of the Sicilian region. The idea was to initiate an articulated study and research activity on the conservation problems concerning the archaeological site and its decorative apparatus. From what has been said so far, it's clear that the location of the Villa Romana del Casale in Piazza Armerina is very unfavorable. The hydrological problems related to frequent flooding events that we have mentioned in the previous slide have always given rise to numerous physical, chemical, and biological problems. All these gave strong motivation to start the project for the recovery and conservation of the Villa Romana del Casale in Piazza Armerina, directed by architect Guido Meli, that is one of the co-authors, in agreement with the High Commissioner for the Villa Romana del Casale, that was Vittorio Sgarbi. Numerous interventions were made in the project, some of which are listed in the photos. Some earthworks in A and B, the works for the construction of the drainage channel downstream of the villa to convey water to the river in C and D, the cleaning of the original drainage channel upstream the villa in E, panel E, and some work aimed to safeguard the masonry in the level F. Okay, after all this, a real stress test was awaited to verify the validity of the work carried out. What better than a Medicane? Medicane is quite a new word that combines the two words Mediterranean and hurricane. The Apollo Medicane, occurred in October 2021, was obviously monitored in all its phases by sensors and weather forecast models. We report here the visualization of a cumulative product obtained from the combined use of the National Radar Network and the rain gauges. The large amount of precipitation falling during the event over central Sicily in the period from 22 to 29 October is quite evident. During the entire analyzed period, the rain gauge of the municipality of Piazza Armerina recorded the total precipitation of almost 180 millimeters, 94 of these in the one day alone, in the 22 October. Cumulative rainfall are here given in this picture. You can see in blue the sub-hourly, in red the hourly, and in green the total. Note that the gray areas represent the real-time data lack. Remote sensing made using satellite data makes it possible to follow at a large scale the events like this one, with images available every 50 minutes from the Meteosat second generation. We show here as an example a sequence of the depth infrared images, one for each of the 9 days from 22 to 30 October. In the afternoon of 22, it was a day when 94 millimeters of rainfall were registered, and the phenomenon evolution is given in panel B and C. In the early hours of 25 in panel D, the cyclone formed close to coasts of North Africa and continued its trajectory in panel E towards the east-southeast until 27th panel F. And October 28 in panel G is strengthening and moved closer to Sicily, reaching its closest point to Italy on October 29. Finally, from October 30, it has definitively moved southeast towards the coast of Libya. Continuous monitoring of the Apollo event was also carried out through the other satellite acquisition and products, precipitation, cloud properties, soil moisture, flooded area. The products that measure precipitation from satellite based on the severe sensor on board of the Meteosat second generation and that are distributed by the Satellite Application Facility in support of operational hydrology and water management, shortly HSAF. This made it possible to follow the evolution of the event also over the sea, and also when no real-time ground-based data were available. In particular, the estimation of surface precipitation is one of the main goals of the HSAF project. Instantaneous precipitation rate, as well as temporally accumulated from 1 hour to 24 hours precipitation, is estimated using both passive microwave measurement from low Earth orbit satellites and infrared data from geostationary satellites. Here we can see the HSAF products that more than others allowed us to follow the evolution of the event. They are named respectively H60 for the instantaneous and H61 for the cumulated. 2 days are shown as an example. Although the heavy rainfall caused the flooded areas and landslide in the surrounding area, the archaeological site under study passed the Apollo Medicane stress test without recording significant damage. So now we can say that the Villa Romana del Casale has been well protected not only from recent meteorological events of medium intensity, but also from the Medicane. MELIS project also envisaged a preventive maintenance plan for the site over time, with the definition of specific program conservation protocols that must be preceded by a careful assessment of the phenomenon and dynamics that characterize the danger of the area and the vulnerability of the cultural site as a whole. Then the archaeological park of the Villa Romana del Casale and the archaeological areas of Piazza Armerina and the neighboring municipalities drew up its first management plan in 2012 and has been updating it since 2020. In this sense, therefore, the management of this UNESCO site is at the forefront in the national and international context. Let's go to the conclusions. The definition of the protocol for the planned conservation of the archaeological site and its decorative apparatus has allowed the mitigation and, in part, the elimination of the intrinsic vulnerabilities and the prevention of further restoration work. Then the management plan for the Villa Romana del Casale, updated from 2020 with respect to the post-restoration edition of 2012, is a fundamental tool for the response of the archaeological site to possible damage from environmental and anthropic causes. This action is fully I hear some echo. Okay, this action is fully in line with priority 4 of the United Nations Sendai Framework, and the evidence of the effectiveness of this management policy was provided by the occurrence of the flood at the end of October 2021, and this exceptional powerful meteorological event in Central Eastern Sicily, those also affecting the area on which the Villa Romana del Casale stands. But for the first time in its history, the archaeological site was not damaged by the flood, which, however, proved disastrous for the city of Piazza Armerina and its surroundings. Thank you for your attention, and I wait for you for visiting the Villa del Casale.
I hope you can hear me. Thank you, Professor Dietrich. And if some colleagues have some consideration, some question, otherwise I have one. Okay, so I will go for that. My wondering is that your work is focused on protecting cultural heritage from water, which really is a difficult task. And I was wondering if you have other case studies, other situation or experience which can be compared to this one, because okay, the Medican was an extreme and exceptional events, but we all know that this kind of events will be more frequent in future. And I have the curiosity to know if you already find some other case study to compare or on which you are currently working.
Okay, there is, I came from the satellite precipitation measurement expertise, but obviously in last years we face many flood cases, and we follow them with Department of Civil Protection. And just the last year to this conference, we present the Matera flood event. And as a matter of fact, this event will be more and more frequent. We need to be used to follow, to forecast this kind of event, to mitigate the effects. This particular case was related to the fact that generally we talk about disasters, we show flooded area, artifacts destroyed. In this case, for the first time in my career, I present one case where nothing happened because some measurements to prevent the damages were developed. So this is the case.
Yes, it's really nice to hear that, and I hope to see to hear more about this kind of success instead of course, disasters.
You.
Any other consideration, question from colleagues?
Just one question. Are each self data open products?
Yes, the HSAF is a EUMETSAT satellite application facility that is built, is organized, is a consortia that created products, and the aim of the existence of the SAF is to distribute data to mainly to meteorological users, but the SAF has open to every kind of users. So just connect to the site, ask the data, and you will be okay.
Thank you very much, Stefano.
Thank you so much. Now I think it's time to move forward with Professor Stefano Federico, Claudia Torcasio, and Mascitelli, and Del Frate, and the same Professor Dietrich. And I hope Professor Federico is able to hear us and present. They will present the results from the AeroMet project on the assimilation of the rain rate from satellite observations. And please, Professor Federico, the floor is yours.
I will present. How can I share my screen?
Okay, so please, Dr. Torcasio, let's go ahead. Thank you.
Can you see my screen?
Yes, we can see and hear you.
Okay. I will present the preliminary results of the AeroMet project on the assimilation of the rain rate from satellite observations. This project aims to assimilate rain rate data into the WRF model and to evaluate the impact of this data assimilation. We're going to see the model and the simulation configuration. Then we will go to the assimilation method to see which method was used for assimilation. And then we will see the results for 2 case studies for winter 2021-2022. And then, of course, we'll go to conclusion and to the future work in the framework of the project. The WRF model we used will have the 3 kilometer spatial horizontal resolution and 635 per 635 grid points. And the domain is shown in this slide and covers the whole Italy, the Central Europe, and part of Northern Africa. You can also see listed the main physical scheme used. And in the figure in the bottom right part of the slide, we see the scheme used for simulation. So we use a very short-term forecast approach with simulation that lasts 12 hours. So in the first 6 hours, we provide a simulation phase, which is represented by red line in this figure, and the second 6 hours are for the free forecast, so the blue line figure. In the assimilation phase, we produce an analysis every 1 hour for the first 6 hours using 3D VAR. So this assimilation is made by 3D VAR assay, and we need to generate a relative humidity pseudo profile, and we saturate this profile between 2 layers, the lifting condensation level and the minus 25 degrees. So we produce this profile where the rain rate is higher than a given threshold. Here we use the 3 millimeters per hour threshold, and we decided to use this threshold after different tests on different case studies and different threshold, of course. The data we use is the rain rate value at the hours in which the 3D VAR is applied. Here we use the H03B dataset distributed by HSAF. We need to pay attention because the variable assimilated by the model is the water-vapor mixing ratio. So we need to convert the relative humidity profile in water vapor mixing ratio before applying the 3D VAR. For applying the 3D VAR, we also need to calculate the background error covariance matrix. And we did this calculation using the NMC method and considering a period in the season in which the case studies occurred. For winter, we consider 15 case studies that are listed here. And for each day, we produced 4 runs, considering that we are doing a rapid data cycle every 6 hours. And we consider 2 configurations, a background configuration without rain rate assimilation and an analysis configuration with rain rate assimilation. In the following, we're going to see the results for 2 case studies. Before applying 3D VAR, we need to interpolate rain rate on the work grid. That's because the rain rate data have a spatial resolution of about 5 kilometers, while the model has an horizontal resolution of 3 kilometers. So in this slide, you can see on the left the rain rate from satellites, and on the right, the same data, but interpolated on the work grid. Here we can see an example of analysis on 2 rain rate thresholds, the 3 millimeter threshold we chose, and another threshold that is the 5 millimeter per hour threshold. We choose the 3 millimeter threshold because it has a wider correction, as you can see also from this example, and is in better agreement with the observations too. Going to the first case study, this occurred on 10 December 2021, and here we consider the phase between 0 and 3 UTC, and we see on the left the H003B rain rate, and on the right, relative humidity field innovation at about 3 kilometers. At the 0 UTC, that is the end of the assimilation phase, we see that the few convective cells over the Tyrrhenian Sea are well represented by the analysis. We are also interested in the impact on the precipitation field. So here we can see the background precipitation field where no rain rate data assimilation is applied, the precipitation field after rain rate assimilation, and the observed precipitation. We can see that the simulation which assimilates rain rate, that is the graphical in the center of this slide, has a better representation of the pattern over southern Italy, so it's in better agreement with the observations compared to the background one. The second case study we're going to see occurred on 15 February 2022, and again we're going to see the phase between 0 and 3 UTC, and here we have the rain rate from H03B and the relative humidity field at about 3 kilometers on the work grid, again at the end of the simulation phase. Here we can see that the pattern on the northern west of Italy is well represented by the analysis. As regards the precipitation field, we have that the simulation which assimilates rain rate has is in better agreement with the observations, and in particular the precipitation over Liguria between 20 and 30 millimeters is better represented and is missed by the background one. Going to the conclusions, we presented the preliminary results of the AeroMet project, which aims to assimilate the rain rates observed from satellite into the work model with 3D VAR. The basic idea is to select areas of convection from the rain rate estimation and to saturate the atmospheric column above those areas. We show the preliminary results for 2 case studies in winter, and these results show the feasibility of the method. Of course, we'll need a larger number of simulations to be considered to quantify the impact of the satellite-derived rain rates on the precipitation forecast at the short term in the Mediterranean basin. Thank you.
Thank you, Professor Torcasio, for your presentation. So please, if some colleagues have some question, don't be shy.
Just one curiosity. Alberico Sonessa from Politecnico di Bari. How do you measure the agreement between the simulation and the measured data? There is an index, I don't know.
Using classical scores, I mean, like frequency bias or probability of detection, repeatable fit score, or false alarm rate, for example. Of course, for this, you need a higher number of cases. These are preliminary results, so we showed only 2 case studies. We're going to study some case studies in all season of the year and got to assess the impact in each season using some scores.
Okay. Thank you very much.
Thank you.
Dario?
Sorry, now you can hear me, I hope. I have a question about how do you apply this study, in the sense that what are the implications for civil protection? You can alert on the what are your plans to use this study in the emergency field, in the emergency organization? There are some procedure, or just it's still a research issue?
Well, here we can predict the following 3 or 6 hours. So just alerting in the last part of the event. If we get with a simulation an event that is not given by the control, we have an added value to alert for a precipitation event that is occurring in the next 6 hours, for example.
And actually, it works. I mean, are you able to run this chain of alert, or not yet?
Not yet with brain rate assimilation. We are working on other kinds of data, assimilation of other kinds of data, like lightning or radar assimilation.
Okay, many thanks for your intervention, and we can now move forward with the final presentation of Professor Bakadaren Narbayev, which will present as a model for wind comfort assessment around tall building. And so, Professor Narbayev, the floor is yours.
Hello, everyone. Can you hear me?
Yes, we can hear you. And
okay.
See.
So, again, greetings to everyone, and thank you for such opportunity. My name is Bakhtarian Narbayev. I worked as a research assistant at Nazarbayev University in Nur-Sultan, Kazakhstan. This paper was written in collaboration with Professor Yerlan Amanbek. Now I would like to present our research in this conference. The topic of our research is finite element model for wind comfort around a tall building. Specifically, we are focusing on the Tower of Kazakhstan. Here is a brief outline of my presentation. I will explain our motivation behind this research, list main objectives, tell a little bit about our methodology and corresponding numerical results. Then I will draw some conclusions and list the references. So what's our motivation? The wind behavior around modern buildings has an impact on humans' lives, as we know. So injuries due to wind are very common, especially in Nur-Sultan, where I'm from. Consequently, pedestrians might avoid certain spots in the city due to wind problem, which leads to the problem of underutilization of parks and other places dedicated to people. So the modeling of the wind effects allows decision makers to take into account human activities at an early stage of the city plan. One of possible ways to reduce the effect of wind is by wind blocking activities, such as planting trees or placing obstacles in places dedicated to pedestrians. In the literature, several studies have used computational fluid dynamics to assess wind conditions in urban areas. Most of results were obtained by various commercial software tools in the study of the impacts of climate conditions, such as wind on buildings. So to investigate this problem locally, we consider a model of the Tower of Kazakhstan. As you can see it at figure 3. The Tower of Kazakhstan located in Nur-Sultan city, Kazakhstan. And the tower is expected to be the tallest building in Central Asia, with a height of nearly 311 meters. If you look at figure 4, the tower is surrounded by 4 small buildings. There is a linear park for pedestrians behind the buildings. The tower is surrounded by 4 streets. From the left, Akhmeshet, Sığanak from the top, Turkestan from the right, and Almaty from the bottom. This will be our domain of the problem. So why particularly we are choosing Nur-Sultan? It's because the location of Nur-Sultan city is in the steppe, and it's very common to have windy weather near the tower. So this leads us to our objectives. In our research, we study the behavior of the wind velocity around the Tower of Kazakhstan by using the time-dependent Navier-Stokes flow model. To examine our model, we used a finite element method with a projection method by utilizing open source DIL2 library. The numerical model was verified by the experimental data. To our knowledge, such a model using computational fluid dynamics has been scarcely investigated for the Tower of Kazakhstan. Also, it's principle to analyze our model from the point of the pedestrians, since they are main clients of the urban environment. Hence, in our research, we associated every obtained result with the wind comfort categories, which are shown here. So there are mainly 6 comfort categories, which are referred to as sitting, standing, and so on. So these categories are defined by the, as you can see, gust equivalent mean speed. In our research, the main focus is on uncomfortable and exceeded categories, the bottom ones, because they are the categories that make pedestrians' lives harder, let's say. Now let's move on to our methodology. To identify wind categories, we compute wind velocity values in the problem domain. For that, we utilized, as I have said, DIL2 and open source partial differential equations numerically by finite element method. Inside the library, we used step 35 case, which allowed us to solve incompressible time-dependent Navier-Stokes equations. Here are the equations. The second equation represents incompressibility or mass continuity condition, and we assume the laminar flow behavior. Also, these equations are supplemented by the initial condition and boundary conditions. So regarding boundary conditions, first of all, we imposed no-slip boundary conditions on the top gamma 1 wall, the bottom gamma 2 wall, and the building itself. On the left vertical part, gamma 3, we set the initial velocity values of the incoming flow. So incoming flow, its x component has a parabolic structure, meaning that the highest value is achieved towards the middle. But at the same time, the y component of the incoming flow velocity equals 0. Finally, we set boundary conditions on the right vertical boundary gamma 4, where the values of the pressure and y component of the velocity equals 0. Now let's move. That's what I have said. So now let's move on to the problem domain. In our research, we consider the Tower of Kazakhstan and its surrounding. Since we conducted our simulations in 2D, we need several views to solve the 3D problem. At a high level, there are only two main scenarios. The first scenario is the view from the side of the building, and the second one is from its top. The domain differs depending on the scenario. So for the side view, the domain consists of the building, a smaller area in front of it, and a larger area behind, which contains a linear park dedicated to pedestrians. For the top view, the domain is similar, except for the bottom and top boundaries. These boundaries correspond to the borders of the building on the other side of parallel streets, Akhmeshit and Turkestan, respectively. In addition, we consider two different corner structures for the buildings, sharp and round. So we generated the mesh for the provided setting, and the code refined it 3 times and prepared it for the Navier-Stokes problem. For the mesh, we used only rectangular shapes. During mesh generation, we constructed finer mesh around computationally heavy parts of the domain, which are mainly the corners. This allowed us to acquire more detailed and accurate information about the wind flow around the building. So the results are here. Here is the final mesh of the side view setting. If we zoom out a little bit, we can see the mesh around the building itself. We used finer mesh around the building and especially its corners. Now these are the final meshes for the top view and two different corner structures. And if we zoom in again, you can see that we have used finer mesh around corners. So the mesh generation parameters are as follows. So very briefly, number of active cells was higher than 8,000. Degree of freedom for velocity are around 70,000 for side view and top view. And degree of freedom for pressure, MH here, is around 8,000, 9,000. So what are our results? Different simulations were conducted in different views to investigate the wind velocity profile in the domain. Also, the total number of the simulations is far more. Here we present only a small portion of it. The main emphasis was put on the parameterization of the different views on the domain, Reynolds number, and the highest magnitude of the incoming flow velocity. We found out that most plausible values are as follows. For Reynolds numbers are 50, 100, and 200. And for wind, these values are, as you can see, the first value is around 5 meters per second. It's the average velocity of the wind in Nur Sultan. and 23 and 28 meters per second are registered velocity values occurred in our city. Finally, we compared the velocity profile in the domain for different corner structures in the top view case. So before conducting the numerical experiments themselves, we needed to verify our model. Here we verified our model qualitatively against commercial sim-scale CFD simulation. As you can see, similarities in terms of the behavior of wind trails and areas of appearance of the vertices. But another approach was to verify our model by comparing it to the laboratory experimental result numerically. We used the experiment results as a reference model and compared it for particular values in vertical line connecting points from 61 to 66. So this is experimental setup, and at these points, velocities were recorded. So in this model, the incoming velocity profile has a parabolic structure. The velocity value rises quadratically. Moreover, the incoming velocity profile has only x component as non-zero, which makes it very identical to that of our simulations. So knowing the inflow velocity profile, adjusting mesh for different boundary conditions, and optimizing the comparison across time steps, we obtained the following results. Orange dots are experimental values, and blue line it's results of our model. So they're indeed in good agreement. Now to the simulations itself. In our first run, we tried a structure that depicts the side view of the Tower of Kazakhstan. Here we are showing only simulation results for the side view with a maximal initial value of 23 meters per second and a Reynolds number of 200. Figure 19 illustrates the results. We can see that placement of such tall building resulted in a vertex just behind it. Figure 20 shows this the same results, but only for X component. Look at dark red spots and towards the near bottom boundary. Here approaching the building in reverse X direction against the wind becomes very hard because the velocity values belong to the uncomfortable and exceeded categories. In the top view case, our focus was shifted. We wanted to examine what type of corners are best to hold velocity of the wind. So again, for Reynolds number of 200 and velocity value of 28 meters per second, we got a maximum value of wind of around 33 meters per second for sharp corners. In the same setting, but with round corners, we got around 31.25 meters per second. So for the round corners, both serve for purpose of holding the velocity of the wind from increasing its value. So round corners are better. Conclusion. So using CFD with a finite element method and open source software, we investigated the problem of wind effects on a tall building, specifically Tower of Kazakhstan. We solved the Navier-Stokes model using the projection finite element method in the DIL2 library. We verified our model, and our numerical results have shown that in some cases, in some spots, wind achieves values that belong to uncomfortable or exceeded pedestrian comfort categories. And finally, we understood that round corners are better in terms of pedestrian comfort. So thank you very much. If you have any questions, do not hesitate to contact via email. And finally, we wish to acknowledge the research grant from the Ministry of Education and Science of the Republic of Kazakhstan. Thank you again.
Thank you, Professor Karen. And
was it too long?
No, it was okay. Don't worry.
Okay.
We are
Sorry.
long because we start in with a delay. And if some colleagues has some question, otherwise I have one.
Please, Dario.
So, yes, I was wondering if a couple of things. First thing I would like to know if this method can account for system of buildings. I mean, not only isolated buildings, but also the interference between the presence of and spatial distribution of different buildings. And if, in your opinion, second question, something could change, or it could be considered the presence of a group of people or crowd streets for, like in the case of public events, if something change and if it could be interesting to simulate that case.
Oh, okay. Thank you for your questions. Actually, the first question is one that we plan to consider in our future work because the Tower of Kazakhstan is actually surrounded by by 4 shorter buildings. But in our research, since we are considering top view, in top view case, they don't affect if we consider higher values of height, let's say, and in side view, it actually might interfere with the results. So it's in our future plans. For the second question, you mean simulating also crowds, yeah?
No, I mean, if from your point of view, the presence of a great number of people could and somehow change the effects of comfortable feelings or uncomfortable feelings, and if it can be accounted in this kind of simulation.
Yes, actually, so in our simulation, we might include certain obstacles or, for example, trees, or as you have said, several people, and they might face the first motion of wind, yeah, and the face of the crowd, the outer layer of the crowd, let's say, will be feeling uncomfortable in this situation, but obviously people which are in the crowd will be okay. It can be accounted, yeah.
Thank you so much for your answer. Are there any more questions?
Yes, just one question. Just considering the side view, is there any way to mitigate the effects away from the tower on the pedestrian?
Yes. So behind the building, so the right side of the side view, in the figure, actually there is a linear park planned, and for sure we'll have trees. And
so you have to put something, a barrier on the ground. Can you can you do something on the structure?
On the structure?
Yes. for example, to put something on the top of the building or something like that. I don't know. I was wondering if something
actually,
in the side shape of the tower.
yeah. I think we might. That's a good idea. We might play with the roof of the building in the side view case. But the thing is that in this kind of problem, wind behaves very unexpectedly. So if we mitigate the risk of uncomfortable or exceeded categories for people in the park, in the linear park behind the building, for sure wind will go through another place.
Okay, very clear. Thank you.
So it's late now, and I want to thank you all the contribution and the contributor, and I hope to see you in presence maybe in next year, because as you know, in presence, ICSA will be more enjoyable, and we have more time to share our visions, idea, research, and this is my hope for the next year, because we will for sure repeat our workshop on RES 23. I don't know if my colleague Alberico wants to say something.
I just want to thank you everyone for their contribution, and me too. I hope to see you everyone in presence next year. I don't know where, but I hope to see you in presence and have a beer with you maybe.
Okay, thank you.
Okay, so good work and goodbye.
Bye.
Thank you.
Thank you very much.
Thank you. Goodbye.
Irene, estás-me
Eu estou-te a ouvir. Estás-me a ouvir?
Ora, fala, Irene. No?
Estás-me a ouvir?
Don't listen that.
Ok.
Just
Ora, fala, Irene.
why there is a
Estou a falar.
There are some feedback here.
Estou a falar. Ouvir?
just try like this.
Estás-me a ouvir, Irene? Não?
Eu estou.
Try now, please.
Irene?
Yes? I hear you.
Ok. Estás a ouvir? Irene?
Eu estou a ouvir. Sim.
Sim, ok. Mas já...
Posso testar?
Yeah.
Estás a ouvir?
Sim, mas
Ó, Graça.
aqui há algum feedback.
Eu estou. Está-me a ouvir, Irene?
No, but
Eu estou a ouvi-la muito baixinho. Vou pôr mais alto. Agora fala lá.
Sim. Está a ouvir agora?
Sim, já ouço melhor. Estou. E também me ouve a mim?
Nós aqui estamos a ouvir. Estás a ouvir, Irene?
Estou.
just a second.
Perdeu o
espera.
feedback, mas...
Espera um bocadinho, que há aqui um problema de feedback. E o assistente não está a conseguir resolver. A Graça está a ouvir.
Eu estou.
Tá? Graça, consegues falar mais alto?
Hã?
Ouça.
Eu estou a ouvir bem. E estou a falar alto, ouvem-me bem? Ou não?
Sim, mais um bocado. Ora, fala, Graça.
Sim.
Ok.
Estás a ouvir? Sim.
Espera só um bocadinho. Sim, eu estou a ouvir, Graça.
Eu estou a ouvir.
Só que a Irene ouve muito melhor do que a Graça, é engraçado. É porque está mais perto. Graça, às tantas vais ter que... Estás aonde? Na Guarda?
Eu estou. Claro.
Então vais ter que ir até Faro.
Está bem.
Espera um bocadinho, está bem? Porque isto aqui há um problema de feedback, ou pelo menos parece aqui. Eu vou só buscar os óculos. Não é preciso, estão aqui. Little bit of feedback.
Just ask for.
I think. Precisa de um? Não. It's online. But remotely? Alguém que tenha o microfone ligado? Graça?
Let's try.
Podes falar, Graça?
Sim, posso falar? Sim. Ouves?
Pois, pois. The PC? No, 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 no. Okay. No. I just asked for the application. Let me try this one. Try now. Can you try? Irene? Estás a ouvir, Irene? Estás a ouvir?
Estás-me a ouvir?
Só que nós não estamos a ouvir a ti.
Eu?
Ok? Agora fala, Irene.
Sim? Sim?
Agora acho que está bem.
Estás-me a ouvir?
Sim, estou a ouvir. Tu ouves? Ok. Estás a ouvir?
Eu ouço, eu não sei.
Graça?
Sim, eu estou a ouvir bem.
Graça? Não.
Estou a ouvir.
Certo. I don't know why this happens. Ok. Just Ok. Sorry, vamos esperar só um bocadinho, está bem? É que isto aqui está com feedback.
Let's try.
Estão a ouvir?
Sim.
Yes, but Graça, if you mute that, if someone talk, estás a ouvir?
Sim.
Sim.
Yes.
Not too low.
Graça, estás a ouvir?
Estou.
Passa aqui um pouco.
Queres muito baixo.
Isso não é problema. We're going to use okay. This is using this, but it sounds low, but I suppose it's no echo now. Can you?
Irene, posso falar um bocadinho?
Posso? Estás-me a ouvir?
No,
It sounds louder. You have to use it.
but I always use the speaker. This is a microphone and speaker.
Yes, I know. So if you want to use this two.
Sure. Yeah. Irene, posso falar um bocadinho? Graça?
Sim.
Ok.
Estás-me a ouvir ou não?
Sim, estou a ouvir. Ouves?
Ouço.
I suppose the first solution.
Okay, let's go start.
Like this?
Yeah, it's not the ideal, but
I think it's less echo with using this.
okay.
So I try. No, that's no. Yeah. No sé por qué son Bueno, you can keep it with low volume and manually.
Okay.
Could be a solution because
Okay.
we don't know exactly
Okay.
what's happening now. Yes.
Irene, podes falar um bocadinho?
Sim, estou aqui.
Ok. Ricardo, vais ter que vir para aqui. Ok? Pronto. Let's go to start. Ok, thank you. Ok, sorry. Ok. Bem, vamos começar. Let's go to start. Nós só estamos mesmo nós. Não sei se podemos falar em português. O que é que achas? Falamos em português ou falamos em inglês? Este Simone...
Não, aqui fora estão vários, são outras pessoas. Anda lá, fala aí, mas despacha isso.
Quem é que está?
Anda lá, Fernando. Começa.
Mas em inglês?
Sim.
Okay. The first speaker is myself. Okay. I will talk about a modified Quaternionic bias trust method. This is a joint work with Maria Irene Falcão, Ricardo Severino, and Maria Joana Soares.
I'm sorry. Are you sharing the screen?
Okay. Yes.
Fernando?
Yes, I'm sharing screen. No?
You are not seeing the screen.
Okay, escape. Okay. Just a moment.
But I cannot see it. No.
Yeah, this one? This one? Yeah. Compartir. Okay. Okay. Now, are you seeing? Can you see my presentation?
Yes.
Yes, okay. So I will talk about quaternionic polynomials, and I will start the presentation talking about a little bit about the real algebra of quaternions. One is the real unity. I, j, k are the imaginary unities, and the multiplication rules are given by these rules here. We can immediately see that the multiplication is not commutative. So a quaternion is an element of this kind, and we call the Q naught is the real part, and we call the next part the vector part, and usually denoted by Q underbar. The conjugate of Q is this element here, and we also endow the algebra of a norm, define it this way. Okay, every non-null quaternion Q has an inverse given by this formula. In H, we define an equivalence relation, saying that two quaternions Q and Q prime are equivalent if and only if there exists a non-null quaternion H such that Q prime can be obtained multiplying Q, HQ, the inverse of H. This equivalence class induce a partition of H, and each class, which we call the conjugacy class, is formed by all the elements that are in the relation, the equivalence relation with Q. So if all the elements of this class, or the similar elements, are all the elements that has the same real part of Q and the same norm of Q. If Q is a real quaternion, then the conjugacy class is singular, with the Q is the only element in the set. But if Q is a non-real quaternion, then the relation, the conjugacy class is a sphere defined as we see here. Okay, so we'll talk a special kind of polynomials. The one side left polynomials are polynomials defined like this, where the coefficient is always in the left-hand side of the powers of x. In this ring, the addition and multiplication are defined as in the commutative case. Given a polynomial p, we call p bar the conjugate polynomial of p, defined this way, and the characteristic polynomial associated with a quaternion Q is a second-degree real polynomial defined multiplying x minus Q by x minus Q bar. Usually, the polynomial, the characteristic polynomial associated with Q is represented by psi Q. The evaluation map is if you want to know the value of P in quaternion Q, is this way. But I stress that the factoring does not preserve evaluation, which means that if we have a polynomial factorized as a left polynomial and a right polynomial, usually the value of the polynomial P in Q is different than, compute L in Q, compute R and Q, and multiply these two quaternions. obvious. We can evaluate the polynomial using the factorization, but in this case, we have to evaluate the polynomial L in quaternion Q tilde that is an element of the same conjugacy class of Q. A zero of a polynomial P is a quaternion such that P of Q equals 0. And a zero of a quaternion is an isolated zero if it is the only elements in the conjugacy class of Q. If Q is not an isolated zero, then it is called a spherical zero of P, and we call this zero as the conjugacy class as a sphere of zeros. A real zero is always an isolated zero, but if a non-real quaternion is a spherical zero, then this is equivalent to say that Q and Q bar are both zeros of the polynomial, and which is equivalent to say that all the elements in the conjugacy class are elements of are zeros of P. A quaternion Q, if a quaternion Q is a zero of P, then this is in fact an equivalence. Then we can factorize P as a Q times x minus Q. If Q is a spherical zero of P, then we can factorize the polynomial P as Q times the characteristic polynomial associated with the zero, the spherical zero Q. A consequence of this result, as a consequence of this result, we can factorize a polynomial P this way, which means that there exist quaternions x1, etc., xn, such that we can write the polynomial P this way. But observe that, that the elements x1, etc., xn are not zeros of Q. They are what we call factors of Q, but we can obtain the zeros of Q. We can obtain the zeros of Q using this relation here. Okay. So I will talk about a modified quaternionic Weierstrass method. The Weierstrass method is a very popular method to compute the zeros of a polynomial simultaneously. And in 2018, we proposed a method that extends the classical Weierstrass method to the quaternionic case. The iterative scheme can be seen here, but I will not talk about this. One important result also obtained in that paper is that if the guesses of the factors of the polynomial are sufficiently close, and if all the zeros are simple, then we prove that the convergence of the factors xi is quadratic. And also the convergence of the zeros, zeta, zi, are the sequence of the sequence of the zeros of zi converge quadratically to the zeros of the polynomial. A simple polynomial, an n-degree polynomial, has only simple zeros if all the zeros are isolated and different. So if a polynomial has a spherical zero, then we cannot guarantee quadratic convergence to the zeros. And so we propose here, we are proposing a method that can be more efficient in terms of convergence. So if quaternion alpha is a spherical zero of P, then we have already seen that we can factor P like this, okay? So what we want to, what we are looking for? We are looking for a factorization of the polynomial P in a product of two polynomials, Q and S, such that the zeros of Q are all isolated and the zeros of S are all spherical zeros. So assuming that P has 2k spherical zeros, Z1, etc., Zk, and the corresponding conjugated, we can obtain that X, the polynomial S, can be computed as the product of the characteristic polynomials of Z1, etc., Zk. Since the polynomial P can be represented using four real polynomials, P1, Pi, Pj, Pk, such that we can write P in this form, okay? So the starting point is to compute all the 2k common complex zeros of these four polynomials. We are calling the set of these zeros Z, okay? Now I will describe the modified Weierstrass method, the algorithm. The first step is to define the monical polynomial P and a tolerance to that we will use in the method. I will illustrate each step of this method with an example because I think in this way is more simple to understand what we are doing. So suppose that we have a 4-degree polynomial P, this polynomial P. The second step is compute the four real polynomials P1, Pi, Pj, and Pk. So P is this polynomial. We can rewrite this polynomial this way, and then we can see that this is the polynomial P1, Pi, Pj, and Pk. Okay, so we have these polynomials. The next step is to find all the common complex zeros of these four polynomials. Of course, we start computing the zeros, the complex zeros of the lowest degree polynomial, in this case, Pj or Pk. So step 3 is to construct the list of complex roots with the imaginary part of the lower degree polynomial P, so guaranteeing that it is a complex zero. And in this case, it's very simple to observe, and we observe that MATLAB finds exactly the roots, plus and minus I, of Pk. Then we will verify if all the zeros, if the I or minus I are, in this case, I is a zero of all the 3 recent polynomials. But here we use the Goetze's algorithm that allow us to compute P of alpha, constructing a factorization, the division of P. So if to say that alpha is a zero of P, it is equivalent to say that C1 and C0 are both zeros, but in this case we have also the polynomial Qn, and in the particular case that we are using, we have here the polynomials Q. So the next step is to construct polynomial Q such that P is equal Q times S, and Q is obviously can be constructed in this form. So Q is this polynomial. And now we will apply the Weierstrass method to the polynomial, the Quaternionic Weierstrass method to the polynomial Q, obtain the list of the isolated zeros. In this case, we obtain the two zeros, 1 minus j and minus I plus k. We can see here the error that we obtain using the Weierstrass method and using the modified Weierstrass method. We also can see that this method gives better results using this 6-degree polynomial. Using the Weierstrass method, we obtain this kind of error, but if we use the modified Weierstrass method, we have much better results. Okay, so thank you very much. Okay, I can interrupt. Okay. Okay. Any questions? So, Grasa, you have the hand. Do you want to say anything? Are you there, Grasa?
Yes, yes. Vamos ver como é que partilho isto.
Okay, Grasa.
Sim.
Okay, can you share your presentation?
I'm trying. Can you see my screen?
Okay, we are seeing Grasa. So you can start when you want.
Yes, good afternoon. First, I would like to thank the organizers for giving me the opportunity to present this talk. This is a joint work with Isabel Cação, Irene Falcão, and Helmut Malonek. Our starting point was the connection of Clifford analysis with the combinatorics highlighted through an adequate multiple power series representation combined with the concept of Appel polynomials. In the construction process of a monogenic hypercomplex exponential function, a special class decay of generalized Appel polynomials is obtained. These polynomials decay admit different representations that lead to the appearance of different coefficients in each one of them. Among these representations are representations in terms of a vector and its conjugate, and in terms of a scalar part and a vector part of a paravector. We have already presented in a paper in Journal of Integer Sequences combinatorial identities based on these two representations. The coefficients arising in both representations form number sequences whose elements are connected in certain cases with other celebrated sequences like Viatoris, Catalan, Jakovska. The aim of this work is to study intrinsic properties of a one-parameter family of non-symmetric number triangles, which arises in the construction of hyperholomorphic Appel polynomials in terms of x and its conjugate. Now I will recall some basics of hypercomplex function theory. We use an orthonormal basis of Rn. CL is the 2 power n dimension Clifford algebra over R generated by these multiplication rules. An element of CL is of this form where alpha A is a real number and EA are products of the elements of the basis. Rn plus 1 can be is embedded in CL in the Clifford algebra by identifying this element of Rn plus 1 with an element of this subspace of CL. This element is called a paravector and has a scalar part and a vector part in this form. Like in the complex case, x bar is the conjugate of x. A function f from Rn plus 1 to Cl is called monogenic if satisfied is the differential equation, where del bar is the generalized Cauchy-Riemann operator. The operator del is the conjugate of the Cauchy-Riemann operator and acts as a hypercomplex derivation operator for monogenic functions. In fact, the hypercomplex derivative of the monogenic function is given by del f that coincides with del not f that is in the same way as the complex derivation of a holomorphic function. Continuing in the context of the hypercomplex function theory, I will recall the definition of Untitled polynomials, which is a generalization of the classical concept. A sequence of homogeneous monogenic polynomials Fk is called a generalized Untitled sequence with respect to the operator del if satisfied these two conditions. Fk is of exact degree k, and del f is equal to k fk minus 1. The polynomials pk referred in the introduction belong to the generalized Abel class that is satisfied this definition. And can be represented in terms of for instance, in terms of paravector and its conjugate in this form, where these coefficients have these values. Here, this notation refers to the Pochhammer symbol, as usual. We have here some examples depending on the dimension n. And we have also the corresponding values for the particular case n equal to. Another representation of the polynomials pk, which is not our focus for now, is expressed in terms of the scalar part and the vector part of the paravector variable. Here, the coefficients involve these rational numbers that are connected for n equal to with the Vietoris numbers. For n equal to, we give, in fact, this sequence, which with the additional first term when this sequence coincides with the one that appeared in a paper of Vietoris about positivity or of certain trigonometric sums. We call this n-parameter sequence a generalized Vietoris sequence. But our interest at this point is to explore properties of the non-symmetric triangle numbers numbers T as K that we arrange in a triangle called triangle TN for short. And here you can see some relations between the elements of this triangle that result from these properties already present and proved in this paper in Opuscula Mathematica. Now we present sums of over entries of rows in the triangle Tn. Some of them are related to the well-known binomial sums. One of them is this one, the partition of the unit, that is the sum of all entries of each row of the triangle is equal to 1. Other result is the sum of these products is this value, which depends on the dimension n. And it is interesting to note that in the limit case, when n tends to infinite, these coefficients have these values, and this result can be recognized as the generalization of this well-known binomial sum. Here we have other sum. In this case appears the square of S. In order to prove this result, we use relations between binomial coefficients and the Bochhammer symbol. And like in the previous proposition, in the limit case, we obtain other well-known binomial sum. Now we consider alternating sums of these products, and we arrive to a connection with the generalized Vietoris sequence. In order to prove this proposition, we start with this equality, and we get the result by combining these two expressions, these two results already proved in this paper of Opuscula Mathematica. This proposition does not contain a sum, but shows the connection with the Pascal triangle once again, this time with the central binomial coefficients. Its proofs follows immediately from the property which relates adjacent elements in the same column of the symmetric triangle. When n tends to infinite, this proposition leads to this binomial identity, which contains the central binomial coefficients. From now on, we will focus on the elements of the main diagonal of the non-symmetric triangle. Its entries are kk with these values. I'm referring to this diagonal. First, we note that for n equal to, all the entries of the triangle are related to the Catalan numbers. In fact, we can prove that the elements of the diagonal are related to the Catalan numbers in this way. And by using this property, we obtain all the entries of the triangle as a linear combination of Catalan numbers. Second, taking into account the definition of Gauss hypergeometric series, and by choosing A, B, and C with these values, and considering Z equal -1, it follows immediately this alternating series of the elements of the main diagonal written in terms of the Gauss series. Of course, if you choose Z equal -1, we have this result. The relation with the Gauss series allows the explicit evaluation of the last series, this one, which is convergent and its sum is equal to. In the proof, we write the Gauss series in terms of the gamma function, and we use properties of basic properties of the gamma function. For the particular case n equal to, the sum of the alternating series is this value. In the proof, you use the relation between the elements of the diagonal for n equal to with the Catalan numbers, and you get the result by applying this Catalan identity, which follows from the generating function of Catalan numbers with x equal -1/4. The following, this proposition shows the relation between an element of the triangle with the elements of the main diagonal. In order to prove this proposition, we start with this property with s equal to k -1, and we obtain this equality. Then, by using the same property with s equal to k -2, we have this one, and combining these two equalities, we have this one, and applying the same reasoning successively, we get the result. For the particular case, r equal 2, we obtain this equality. That means the sequence of the elements of the first column is the binomial transform of the main diagonal sequence. Now we consider the sequence decay of alternating partial sums of elements of the main diagonal, and we have this proposition that provides a recurrence relation for the sequence decay with these initial conditions. In the proof, we use these two relations combined with the property that relates adjacent diagonal elements in the diagram. The sequence decay, when n tends to infinite, is related to the Jacob-Stahl sequence. I recall that this is the explicit Jacob-Stahl sequence, which can be generated by its linear form in this way. I have already referred that when n tends to infinite, the elements decay, the elements of the diagonal, are equal to power minus k. And now the relation between these numbers, decay, with the Jacob-Stahl sequence is expressed in this proposition. To prove this proposition, we use this fact, decay equal to power minus k, which leads to a sum of k plus 1 first elements of the geometric sequence which combined with the linear form of the Jacobson numbers leads to the result. Considering this proposition and this recurrence satisfied by the Jacobson sequence, we obtain a simple recurrence of order 2 with the constant coefficients for decay in this way. I have some references used mainly this first one. And thank you for your attention.
Thank you. Yes. Thank you, Graça. Any question or comment? Okay. So, if it's not the case, let's thank again. Thank you, Graça. Okay. Next speaker is Ricardo Severino.
Thank you very much. The title of my talk, well, I will talk about, my intention is to talk about cubic quaternionic maps. The idea is to talk about dynamical systems over quaternions. This is a joint work with Maria Irene Falcão, Fernando Miranda, and Maria Joana Soares, and I would like to begin this talk by saying that this is probably the most interesting topic of this century in mathematics. Yes, quaternions were introduced by James Cockle just a few years after the work of Hamilton, and this is a four-dimensional algebra, and the product, well, I wrote the product as like that, just because. But I can say that in our papers, we do not use this kind of formalism. We use the usual formalism with the unities, etc. Okay. I will not focus my talk on the details. You can look at the details in our papers, for instance. And the idea, in the first minutes, I will introduce some details, some technical details. Then I will talk about the results, some results that we already obtained for quadratic polynomials. And I will start my talk from that moment, and you'll see what I have for you. Well, the conjugation of a quaternion is it's more or less the same as my colleague Fernando Miranda talked about the conjugate of a quaternion. We have the determinant of a coquaternion, and we just say that coquaternion is invertible if and only if its determinant is non-zero. In that case, we can write the inverse of the Q of that coquaternion as this ratio, and you can see why we have to. Okay, just some more technical detail. We can define an equivalence relation in H coq just by saying that Q is similar to a coquaternion P if there is an invertible coquaternion such that P is it's given in this way from Q. This is an equivalence relation partitioning H coq in the so-called similarity classes. We have here, just for the notation for the similarity class containing Q. Okay, next I have a result saying that the following: if Q is a real coquaternion, then the similarity class is just the set of Q. Please remember that if Q is a real coquaternion, then Q is just equal to Q naught. But if it is non-real, we just say that the similarity class of Q can be given in a canonical way by this QS, the representative of the similarity class. And this we have to choose according to this R that is defined over here. Okay. Next, I have here the graphic representation of the non-real part of a similarity class. Just please, see that Q0, the real part of the all coquaternion similar to Q, are always equal to Q naught, to the real part of Q. So this is constant, but that's why it is interesting to see the representation of the non-real part of the similarity class Q for different values of this parameter R. We have here a two-sheet hyperboloid, a cone here, and a one-sheet hyperboloid over here when we have R negative. Okay, let me just do the following. Okay, I have here the results we obtained for the fixed points of quadratics, a special case of family of quadratics given by Q squared plus C, with C a parameter, coquaternion parameter. And the point here is the following. Let's look. The point here, the most important thing is that the fixed points are no longer isolated points, but can be sets of fixed points. And this is what happens here. For C, for certain values of C, for C, C naught, sorry, let me just say something. This is valid for C equal to C real, a real parameter. We proved already that for values of the parameter C non-real, then there are no fixed points of F. But for C, a real parameter, we prove that there are three situations according to the value of C naught, and but the important thing is the idea that we can have sets of fixed points. This is This is a very, very interesting situation, a very, very different, something very, very different from the dynamical systems one was used to, I mean, complex dynamical systems, for instance. Okay, I will go to the next slide, and here I have the following. This was published quite recently, and we studied the quadratic family of polynomials, q squared plus b times q, where b here is our Quaternion parameter. And for this family of quadratic maps, we prove that for b of this form, there are two isolated fixed points, but for b equal to b naught plus b2j, we prove that there are two lines of fixed points. And this is something that we haven't for the other family of quadratics. And this is very, very interesting. We could obtain also the expressions for for both lines of fixed points, and two additional isolated fixed points, Q1 and Q2, with these expressions. Okay, let me. Next, I will do the following. I'm going to ask the following question. Why is the study of fixed points for cubic Quaternionic maps? And the first slide I have for you is to say no. No, maybe it's not the time to go to study cubic Quaternionic maps, fixed points for cubic Quaternionic maps, because it is quite obvious that there are a lot of other families of quadratic maps which need to be studied. And the result is it's something like that. Due to non-commutativity of the product of quaternions, we can say that a general Quaternionic quadrat has the following form, and no conjugacy equivalence to a simple form is known. This means that naturally there is so much work to do with quadratic Quaternion maps that maybe it's a little bit too much to start to study cubic Quaternionic maps. Okay, let me skip the following. And okay, I have here a second slide saying that, okay, maybe it's too difficult to study fixed points for cubic Quaternionic maps. And the idea is the following. What we are looking for are the fixed points of a map, but that corresponds to the analytical solution, to look for the analytical solution of the zeros of a polynomial equation, which can be very hard and a very hard problem to solve. And naturally, even harder as one considers polynomials of higher degree. This means that maybe it's not the time already to go and study cubic Quaternion maps. But let me, okay, I have here something very, very intriguing. The idea is the following. As I showed you before, we can see that the fixed points obtained for both families of quadratic maps show no coexistence between hyperboloids of fixed points and lines of fixed points. And this is something that you can ask if, naturally, if there is something that occurs for every polynomial. And so the idea is maybe we can study an example of a family of cubic Quaternionic maps just just to trying to not to prove, but to see if this non-coexistence of hyperboloids and lines of fixed points are also true for for polynomials of degree larger than 2. And this is because maybe there is no coexistence because of this result we proved in 2019. And the idea is that we have the results say the following: the number of zeros of a unilateral polynomial of degree n is at most n times 2n minus 1. This means that for ni equal to 2, the number of isolated zeros plus the number of sets of zeros cannot be larger than 6. But see, when we go to the cubic polynomials, this 6 is it's much. This number is much larger. It's 15. So maybe this non-coincidence that we see for quadratic maps is no longer valid for cubic maps. So the idea is that maybe just to see if this non-coexistence fails for polynomials greater than 2, it's something that motivates us to study cubic quaternionic maps. Just one more slide, and the idea is the following. For those two families of quadratic maps, we found that there are fixed points, that there are lines of fixed points, and that there are hyperboloids of fixed points. But in this paper, we prove that for C of this form, we have a circle of periodic points of period 2. So this means that what I'm writing here, fixed points, circle of periodic points of period 2 are fixed points of the quartic polynomial that I wrote here. So this means that we know already that there are some sets of fixed points for polynomials of degree equal to 4. But let's not forget that this is a polynomial that is no longer a unilateral polynomial. This means that let's say our methods, our not so simple but not so hard also methods of finding the solutions, the zeros of polynomial unilateral polynomials, those methods cannot be applied here for this non-unilateral polynomial. Okay, let me start my talk now, and the idea is the following. I have this slide. It's a very, very strange slide because we choose to study the fixed points of this 2-parameter family of quaternionic cubic maps. And this is very, very, very strange family of maps. I think no one that studies dynamical systems would choose something like that, but I have here for you the justification. The idea is the following. The fixed points of F of this family of 2-parameter family of maps, look at this, the zeros corresponds to the zeros of P, and if you do the computation, you can see that P can be, it's a simple factorized polynomial. P can be written as Q minus A. A is the first, let's say, it's the first parameter, times Q minus B. B is the second parameter of Y. Okay, why this is fantastic? Because we know that if q times q minus b, it's a right factor of the polynomial p, we know that its zeros are always zeros of p. And look, this is, therefore, the fixed points of the quadratic, let's say q squared minus b plus 1 times q, and this is more or less the same family. It's just a rebranding the parameter. This is something that we already studied, and we know already the fixed points for those maps. So the idea is that we are studying cubic polynomials, the fixed points, the zeros of a cubic polynomial by knowing that the zeros of a certain polynomial is we already know the zeros of that right polynomial, quadratic polynomial that we have here. So let me just stress this. This is very, very important. This idea is important to highlight the richness of the dynamics of cubic or quaternionic maps when compared with the dynamics of quadratic or quaternionic maps. The idea is very simple. We can compare the zeros of this, or the fixed points of this quadratic polynomial, and then we can compute the fixed points of the cubic polynomial that we get by left multiplication by q minus a, by the monic polynomial q minus a. So this is a this is a situation, let's say, that it's very, very interesting in the sense that it enables us to compare the results that we have already for quadratic polynomials with something that a cubic polynomial that we construct in this very, very simple way. Okay, I think my time is okay. Let's say I have an example for you here, and the idea is that for this parameter choices a and b, the cubic map f that we have, we prove that has 5 isolated fixed points and 4 lines of fixed points. This is very, very interesting. If you compare with the results I described for the quadratic polynomials, the idea is that we have a lot, the number of zeros, it's greater, it's a lot. Okay, but the most important is the second example. And the second example I have for you is the following. For this parameter choices, we prove that the map has 3 isolated fixed points, 4 lines of fixed points, and 1 hyperboloid of fixed points. This means that for this family of cubic, so simple, we could already say that the idea of non-coexistence of lines and hyperboloids of fixed points is not valid. Maybe it's valid, we don't know, for quadratic polynomials, but we have here an example showing that for cubic polynomials, there are no problem of having lines and hyperboloids of fixed points. Okay, I'm going to skip everything. Let me say the following. This is our results. We have here. I have here the results. This is something that this is the fixed points of the quadratic polynomial. 2 fixed points, isolated fixed points, 2 lines of fixed points. This notation means that, and by multiplication of q minus a, we get 3 isolated fixed points, 4 lines of fixed points, and 1 hyperboloid of fixed points. This is how this is how we read this table of the results. This is the, let's say, the generic situation, and I have here also some special cases. Okay, and I'm going to finish just by showing you the results we got for you. A lot, and this is something that it's already promising something. This study of the fixed points of cubic maps. But let me just go back, and this is our last slide. The idea that these results that we are here presenting are just for the parameter this parameter b equal to b0 plus b2j. The idea is that there is some work to do for other values, other values of the parameter b, and but well, I can confess that maybe we don't. The results we'll get will not be as good as the second example I show you. Okay, thank you very much.
Are there any questions?
No, it's all right.
Say it again. So.
Okay. So let's thanks again, Ricardo. Thank you.
Yes.
And now the last talk, Maria and Falcão. Can you share?
No, I'm not. I cannot share.
You cannot share?
No.
Sorry,
Okay. Are you see?
Yes. Full screen. Yes.
Can you see?
Yes, perfectly.
Yes.
Yes.
Can I start?
Yeah, you can start, please.
Yes. First of all, I'm really sorry not to be with you in the room. I think probably I'm the only participant that is in Malaga making the talk from the hotel. But never mind. I hope that there is no problem with I'm going to talk about the zeros of quadratic quaternionic polynomials. As you have this session on computational and applied mathematics was all about quaternions, coquaternions, Clifford algebras. Quaternions and coquaternions are also Clifford algebras. So I would like to start probably by are you seeing?
Yes, we are.
Can you? Yes.
Yes.
Probably by pointing out the main difference between the quaternion and the coquaternion algebra. So both algebras are generalization of the algebra of complex numbers. You have here three imaginary units. In the case of the quaternions, the three units square to -1, whereas in the case of the coquaternions, just the first imaginary unit, I, squares to -1, and the other two square to 1. Here you can see the non-commutative nature of both algebras. So this is, you have already seen in this afternoon. This is like as in the complex case, you have the conjugate, the real part, the vector part, the norm, usually use the designation norm in the case of quaternions and determinant in the case of coquaternions, but this is not important. What is important is that this is obtained by multiplying Q by its conjugate. What is very, very important is that in the case of quaternions, just as in the case of complex numbers, the determinant of the norm is always a positive number, a real number, and it's equal a non-negative real number, and it equals to 0 if and only if Q is equal to 0. But in the case of the quaternions, we can have quaternions with negative and you can have quaternions with determinant equal to 0, and
Irene?
the difference
Irene?
from 0, and this all the difference. So,
Irene?
yes.
You are not anymore sharing the presentation. Can you share again? Okay. Okay, we are seeing the presentation already. You can push. Microphone is off. Turn on the microphone. Okay.
Now?
Yes. Okay.
Thank you. So I'm sorry, but I lose my connection. So this, let me skip this this slide. We, in case you have already seen that we can define two different equivalent relation. In the case of the quaternions, both equivalence relation are exactly the same, but in the case of coquaternions, this is not the case. So I'm going to call similarity to this kind of relation where a quaternion is said to a quaternion or a coquaternion is said to be similar to another. If it can be written, it can be written in the form. Can you see when I point out? No.
Yes, we see. We see the hand.
Yes. Okay.
Yes. Yes.
Okay. But in the case of class similarity, this is almost the same. The only difference, as Ricardo has already explained, is when the coquaternion is a real number. In such case, the two notions do not coincide. So geometrically, the equivalence classes in H are spheres in the hyperplane x0 equals to q0, and in the case of coquaternions, they are hyperboloids. Okay, the characteristic polynomial of a class is the 2-degree polynomial with real coefficients given by this expression here. Because this is a real polynomial, this means that we can compute its roots. They can be complex conjugate or they can be real. So this means that the characteristic polynomial can be written in one of these forms. But what is more important is that reciprocally, if we have a real second-degree monic polynomial, this means that this polynomial is the characteristic polynomial of some class. It depends on the roots of Q. If they are conjugate, then it is the characteristic polynomial of this class here. And if the roots are real, it is the characteristic polynomial of this class. So, as Ricardo explained, we start studying the quaternionic algebra motivated by our interest in study dynamical system in this kind of settings. But to do that, we had to study first polynomials in more general polynomials. I mean, not general, they are unilateral polynomials, but general degree. So we start studying such kind of polynomials where the coefficients are located in one side of the polynomials. In this case, we are using left polynomials, but the coefficient can be also located on the right. It's exactly the same. And the addition and multiplication are defined as in the complex case. The zero of a polynomial is defined in this way. And the conjugate of the polynomial is the polynomial that we obtain by conjugating the coefficients of the polynomial. And the companion polynomial is the polynomial that we obtain by multiplying p by its conjugate. This means that this polynomial is if p has degree n, this polynomial has degree 2n and is a real polynomial. This means that all the coefficients are real. In 2019, as I already mentioned, we decided to study this kind of problems that arise in the ring of co-quaternionic polynomials, and we have proved that if a quasi-similarity class contains a zero of p, then the characteristic polynomial of this class is a divisor of the companion polynomial. But the converse is not true. It can sometimes we can have the characteristic polynomial can be a divisor of the companion polynomial without having any zero at all in the class. And this motivates us to introduce this definition, the definition of admissible class. A class is called admissible if the characteristic polynomial, its characteristic polynomial is a divisor of the companion polynomial. In the case of the quaternionic polynomials, the admissible classes are the ones containing zeros of p, and in the case of co-quaternionic polynomials, these classes, the admissible classes, are the ones which may contain zeros of p. What we know is that if there are a zero, the zero is on an admissible class, but no more than this at this moment. So this is the way we can compute the admissible classes. It's just to construct the companion polynomial, compute the roots of the companion polynomial, and then using the results that I have already shown you, you can have these are the admissible classes. This means that if there are zeros, the zeros are in one of these classes. If you count the classes, you come to the conclusion that the maximum number of admissible classes is n times 2n minus 1, as Ricardo said in the previous talk. In the case of the quaternionic polynomials, the maximum number of admissible class is n. Okay. In 2018, we we have results from this paper. This is another adaptation of a very well-known algorithm introduced by Niven, where he studied equations on quaternions. We made all the adjustments and we got these results over here. If we have an admissible class of P, compute all the admissible classes of P, and then determine the remainder of the division of P by the characteristic polynomial of each of the admissible classes. Since this is a second-degree polynomial, the remainder is a first-degree polynomial. And then what we have proved is that the characterization of the zeros is done in terms of the values of A and B. If the determinant of B is different from 0, then we know that in these admissible classes, there is just one zero. For the moment, it is not important how we compute the zero. And this is called an isolated zero because it's the only zero in this class. If A is equal to B equal to 0, then all the elements of the class are zeros of the polynomial. And if you recall that geometrically this corresponds to an hyperboloid, we have called this zero hyperboloidal zero. But the interesting part is the third one, where we can have B different from 0, but with determinant equal to 0. This means that B is not 0, but it is not invertible. And in this situation, we can have two possibilities. The first one is that the zeros of P form a line, and this is the reason why we have called this kind of zeros linear zeros, or we can have just 1 0 in the corresponding admissible classes, which is going to be an isolated zeros. In all the other conditions, in all the other situations, there are no zeros in the admissible class. So this is the general case. This works. Theoretically, this gives us an idea. This theorem helps us to characterize the kind of zeros that we can have, isolated, linear, and hyperboloidal, but it's very difficult to apply these results for general degree. So because we were interested in studying the dynamical of quadratic, at that time, quadratic maps, we decided to apply this result in the case of n equals to 2. And this simplifies a lot, of course. And because now we have P is of degree 2, the characteristic polynomial is of degree 2, so we don't need to perform the division. We just need to do this subtraction, and then we can look and have immediately the value of A and B and apply the theorem. Now, this is written in a more simpler way, but this is very easy to apply this result. So this is what we can do with the results of 2018. Now what we have done, but this result just say that we know that the numbers of zeros is, in the case of the quadratics, is less or equal than 6. But we don't know how many linear zeros, how many hyperboloidal zeros, and how many isolated zeros a quadratic map can have. For example, in the case of the Quaternion polynomials, we know that the number of isolated zeros plus 2 times the number of spherical zeros is less or equal than n. Here, we don't know what's happened in the general case, and in this paper, what we have done is to study what can happen in the case of n equals to 2. So, and the situation is the following. We have proved that, having in mind the results that I have shown you, we have proved this first theorem here that says that if we have an hyperboloidal zero of P, then the companion polynomial has two double roots or one real root with multiplicity 4. If a similarity class contains a linear zero, then the roots of the companion polynomial are all real, and at least one of them is also a root of P. And finally, we have proved that in the case of quadratic map, it's impossible to find a polynomial which has both linear and hyperboloidal zeros. If you remember, Ricardo had shown a case of a cubic polynomial where this was not true, because with an example, this shows. But in the case of quadratic polynomials, this is not possible. We cannot have linear and hyperboloidal zeros all together. So what we have done in this paper, I'm going to skip all the details, is to study the factorization of the companion polynomial and because the roots of companion polynomials are the admissible classes, and then study with all the situation. For example, the first case is where we have two complex roots, and in this case we have proved that we have one hyperboloidal zero or two isolated zeros. This is the situation. In the case where we have one complex root and its conjugate, of course, and two real roots, then there are at most two isolated roots, nothing more than this. And then now the cases, we have more cases where the roots are all real. We can have all these roots. If the roots are all equal, then we can have one hyperboloidal zero or one linear zero or one isolated zero. And we have studied all the cases. I'm just going to show you the table with the summary. So you can see here, this is the situation. The maximum number of zeros, which is 6, can be obtained just when you have isolated zeros. You can have 2 linear zeros and 2 isolated zeros, not more than this, not 2 linear zeros and 4 isolated zeros. No, this cannot happen. And so our conjecture is that in the case of the co-quaternionic polynomials, probably the number of isolated zeros plus twice the number of linear zeros plus 4 times the number of hyperboloidal zeros is less or equal than the number of zeros that we have already proved that a polynomial of degree n has. So I think it's all. Thank you very much for your attention.
Thank you very much. Are there any questions? No. Asa, can you put the camera, Irene? Yes, okay, we are seeing you. Okay, so let's thank all the participants. Thank you very much. And, okay, bye-bye.
Bye-bye.
Bye, see you.